Hello from the Forcetronics YouTube channel and welcome to designing a solar and lithium ion battery powered charger / power source. And this is part 2 in a 2-part series. Before I get started, I'll just say please support Forcetronics on Patreon where you can find exclusive content, including exclusive content from this video series. If you haven't already, please subscribe to the Forcetronics YouTube channel. And if you like what you see here, please hit the thumbs up. All right, let's jump in. All right, as you can see by the length of this video, we have a lot to cover in part 2. So I'm not going to do much of an introduction. I'm going to assume you saw part 1. In part 2, we're going to look at a demo of our design in action, and I'm going to show some example measurements so you get an idea of how everything is working. Then we'll jump into the circuits that we didn't cover in part 1, the isolation circuit, and then the battery charging circuit, where I'm going to spend the most time. And then we'll look at the PCB layout, and then we'll wrap things up. And of course, all the design files, the BOM, things like that can be accessed on Patreon. All right, let's look at the demo. Okay, here's a close-up of our board, the solar battery charger and power source. And so the white cable is the output power, or the output 5 volts. The other cable is the input power. Now, neither of these USB cables are plugged into something right now. And so you can see these 2 lights are on. So these lights mean power good and battery is charging. So this white connector with the red and brown and black wires is our lithium ion battery. And then this screw terminal with these other cables is our solar panel. Now I'm inside my lab, so I'm using a power supply to simulate the solar panel. I'll show you a picture later of the solar panel in action. So we're going to simulate the solar panel. So I have a power supply that's simulating the power from the solar panel. It's on right now, and that's why we have our power good light. And then our battery is also not fully charged, so it's charging, and that's why we have this other light on. And then these other wires are for the thermistor, which monitors the temperature of the battery, and the charging circuit will shut off charging if the temperature is out of range. And then this black and red clip is connected to a DMM to monitor the battery voltage. All right, these other clips are the power supply. Now I'm going to go up to the DMM, and this is the battery voltage. And you can see it's slowly rising because the battery's charging. Now this is the power supply. Notice that the power supply is set. So this is a high accuracy measurement power supply that can measure voltage, current very accurately. I have it set for 4.8 volts and 130 millivolts. So I'm sort of simulating the solar panel, not when it has full sun. And the idea is the way this charger works, if you remember the solar panel output curve that I showed in part 1, is if you try to draw too much voltage, you're not going to get a lot of current. So the way this charging circuit works is it will actually adjust its input impedance to try to get the maximum current out of the power source. And the designers made this with solar panels or solar cells in mind. When it's getting plenty of current, it won't mess with the voltage level. It'll just have a real low impedance, and it has a max current setting, which we'll discuss later. But the idea here is I have a 4.8 voltage limit, but the input impedance of the charging circuit is tuning it to get the max current, and it's going to keep the voltage just above the battery voltage. For this power supply, the current will stay the same, but in a solar panel, as the voltage goes up, the current will most likely drop because you're changing your position on that solar curve, if you remember from part 1. So that's an important concept, an important feature of this charging IC that we'll talk about more later. Okay, now let's plug something in to see the battery charger now in action, or I should say the power source in action. So I'm going to push this, I just pushed this white cable into this headlamp, and we can see this red light means it's charging. So not only now is the power supply or our solar panel providing power to the battery, now the battery has to provide power to this device to charge it. So if we go back up, we're going to look now at the DMM again. Notice the battery voltage dropped by over 100 millivolts. So it used to be at about 3.9 volts. That's because it had no load on it. Once you put a load on a lithium-ion battery, its voltage will typically drop. The device it's charging is pulling more power than the solar panel is providing. So what's going to happen is we're going to see the voltage of the battery drop. So now the voltage of the battery is dropping. And if we look here, the power supply, which is representing our solar panel, its voltage drop, right? Because that charging IC is going to modulate that input impedance to try to keep the max current coming in. And since the battery now has a load on it, its voltage dropped, so the charging circuit adjusted so the voltage of our power source dropped as well. Next, we're going to plug in USB input power. So I'm going to plug in this cable. And now we have a situation where the battery voltage is rising. It's rising rapidly, right? And that's because the way this circuit is configured is the USB input power cuts off the battery power to the boost regulator. So now the USB input power is powering the boost regulator and charging my headlamp. At the same time, it's also feeding power to the charging circuit. It cuts off the solar panel power, and now it's feeding to the charging circuit. So now the USB power, because it has much more power than the solar panel, is charging the battery as well as providing power to the load. So we can see it charge. We can see that that's still charging. And the important thing to notice is the solar panel is providing very little current because it's essentially cut off from the circuit and everything's running off the USB input power. So that's to give you an idea of how everything's working together. Now, since I did my demo in a lab, I was not able to use the actual solar panel because I don't have enough light. So I did want to at least show a picture to show you that this does work with a solar panel. So if you notice, I have the solar panel hooked up. You can see the battery with the thermistor. And I'll talk about the thermistor a little bit later, but a thermistor is basically a resistive device that varies with temperature. So I have this outside on my front porch. We can see the power good and the charging light are on, and we're charging some of my earbuds. So let's look at the remaining schematics in my EagleCAD software. Okay, this is where we left off in part 1, talking about the USB connectors. So I'm not going to touch on that. And of course, I have videos that go into more detail on that. What I do want to talk about is the connectors and a little bit of the isolation, and then we'll jump to the charging circuit. So one thing I want you to be aware of is we have various power buses in this design. And I want you to remember them because they're important when we look at the charging circuit. So VDD is the input USB power, which should be about 5 volts. And it's going to always be isolated from the other power sources by these diodes. And these are Schottky diodes, so they have a low voltage drop. So when USB input power comes in, D2 forward biases, and VCC is the bus which represents the input to the boost converter. So it shares this bus with the battery. And of course, when the USB power is applied, the battery is going to be cut off, and we'll see that on the next schematic. Then we have this other diode, D1, that goes to the charging power bus. And this is a bus that it shares with the solar panel's input. And of course, we'll see on that input that we have ways to cut off the solar panel. But the idea here is, since the USB input has plenty of power, I'm just using simple diodes to isolate it. And so when USB power is not applied, these diodes will be reverse biased by the battery power and by the solar panel. So we don't get any stray voltage or power on this connector that someone could shock themselves with or something like that. We're just trying to avoid that. And then below I have some of these other connectors. So the screw terminal connector where the solar panel was connected is right here, J4. And that represents the solar panel's input bus. So it says solar power. And once again, remember this for the next slide. These 2 pins are just another way to access the output of the boost converter, which is our output of 5 volts. We have, of course, the USB connector, but we have 2 pins in case you want to access it that way. Then down here, we have our battery connector, which is just 2 pins. So BAT connector is the battery input bus. And then I have another just 2 test points so I can monitor and check the battery voltage. And that is on the same bus, battery connector. Now, if you remember from part 1, I showed you a second prototype board where I had a mechanical switch. That mechanical switch, the purpose of it is if you're using this design for like camping trips, where you use it every couple months or every 6 months or something, to charge your phone while you're out at your campsite, and the battery is being charged by solar. If you put this in the storage, you need to disconnect the battery because the boost converter will consume a tiny bit of power over time. and it'll drain the battery down to its lowest level. If you want to just protect the battery and not have it discharge, you can then use that mechanical switch to shut it off when you go to store the design. On the other side though, let's say you're using this to power some sensors in some type of Internet of Things application that's outdoors, and the solar panel and the battery are serving as your constant power source, and your design needs to always be on. Then you don't really need that mechanical switch. So this connector is just a generic 2 holes that I put in for a switch that I grabbed out of my lab stock. If you want to put in a fancier switch, you just need to change this footprint. But that's the purpose of this, is it isolates the battery input from the output of the charger where the battery is charged. And this is optional. If you want to use the board as is, you can just put like a shorting wire across it. Okay, now we're looking at the charging circuit where we're going to spend the most time. So the charging IC from Texas Instruments that I'm using is right here. So it's the BQ24210DQC4, and that's labeled U2. So we'll get into this. But let's work our way over from the solar power input and these isolation circuits to the charger to the battery connection. Because we have sort of a intricate setup for isolating the solar power, right? And so here's that solar power input that comes from that connector I just showed you. And I could have just put a Schottky diode here that basically isolates that solar power input for when the USB power is connected. And the USB power comes in here at this charge power node, if you remember from the last schematic. I could do it that way. The problem with the diode is the solar power voltage can actually be higher than the USB voltage, which that means we wouldn't get good isolation from a diode. Also, the solar panel is, my weakest link in this power chain. It doesn't have a high power output, so I don't want to waste a high voltage drop on a diode. So instead, I'm using 2 back-to-back P-channel MOSFETs, Q1 and Q2. And the way this works is if we do not have solar power applied, and remember, solar power applied is the VDD bus, what happens is the solar power will pull up Q3's gate. So Q3 and Q4 are N-channel MOSFETs, Q1 and Q2 are P-channel. And what that'll do is that'll turn on this N-channel MOSFET Q3 because the source is connected to ground and we put the gate more positive than the source. This essentially shorts this node to ground. And if you notice, this is labeled P gate. So this is the same potential as this other label, P gate, here on Q1 and Q2. If you remember, in Eagle software, if you have the same name, it's the same as having a connection here. So making the gate low and the solar panel power makes the source high. If the gate is more negative than the source, we turn on Q1. Right? So we're going through here. We have these pull down resistors. We're going to turn on Q1, and Q1 has a very low resistance. So we'll get very low voltage drop and we'll get to this bus with our power. Well, remember, MOSFETs have a body diode. So this power will forward bias the body diode of Q2, get to the source, and then of course make the source more positive than the gate and turn on Q2. And now we have a path for current to flow from our solar panel to the input of the charger with very low loss. Now, if all of a sudden we plug in the USB connector for USB power, what happens is VDD goes from low to high because this is the bus where the USB power comes in. Now all of a sudden we turn on this N-channel MOSFET, which then no longer pulls up the gate of Q3. So Q4 is going to turn on, which is going to turn off Q3 because the source and the gate are going to be at the same potential, which then is going to in turn shut off these P-channel MOSFETs because the gates are going to no longer be at a low potential. So that's how we isolate the USB power from the solar power. And the USB power, of course, is the dominant power. If you notice, I have these 3 test points. This was just for me when I was developing it to make sure I could check my signals and make sure everything was working right. If you want to modify this design, you can always delete these test points. Here we have a capacitor that just handles, makes sure the voltage is stable going into the charger. Now for the charger, how it works and some of the pins, I have these notes here. And of course, Where did I get these notes? I read the data sheet for the charger IC, which if you want to modify how you're using the charger, you might have to do it yourself as well. The first thing though I want to point out is setting the current. So the charging current for the battery, you can set it to different values. So you can control the speed of how fast you charge the battery. So the data sheet just gives us a simple equation where it gives you this constant value of 390. Divide that by a resistance that you want to get the current that you want. And of course, you can always do algebra and rearrange this, but I'm using a 680 ohm resistor, R1, which is down here, and that gives me a max charging current of about 574 milliamps. Of course, the solar panel can't put out that much current. So the charging circuit's smart and it'll regulate based on what the power source can put out. And that's one of the values of this charging IC. But when I plugged in the input power of the USB, we were getting that 500 milliamps, or at least close to that 500 milliamps. So that's how we set the max current, the max charging current of the design is R1. Next, let me talk about the temperature monitoring. So the notes for that are down here. So these two connectors represent where you saw that thermistor connected. And like I said, the thermistor, if you're not familiar with thermistors, I encourage you to look into them, but they're basically a resistive device that varies in a known way based on the temperature they're exposed to. So you could apply a voltage source to them, monitor that voltage drop, and then know what temperature it is. And that's essentially what this design is doing. Now, you can use various thermistors out there, and there's various kinds of thermistors. The one I'm using, I'm showing right here, and it has a known sort of set resistance or starting point resistance at room temperature. And so using an equation from the data sheet, I calculated RT1, and R17 is RT1, right? So I get this value, and this is a strange resistance value, so I just pick a value that's close to it, 21.5 kilo ohms. And I'm actually doing this exactly how they do the example in the data sheet. And here's the part number of the thermistor I'm using. So the charging circuit is just looking for a known resistance value here so it can know what thermistor you're using to measure that voltage drop. And basically, if the temperature gets too high, it'll shut off the current charge. If it gets too low, it'll shut it off. And I don't have those temperatures memorized, but you can find them in the data sheet. Okay, another important feature that I need to talk about for this charging circuit is related to its ability to adjust its input impedance to deal with a power source that maybe doesn't have a high power output that what we want to use to charge the battery. Once again, like a solar panel. Well, that's related to this dynamic power management capability that the chip has. That's what the company TI gives the name for it. And that's related to this VDP pin, which is pin 9. You can put a resistor on that pin to kind of set the minimum voltage. But if you leave the pin floating, which is what I did, it will dynamically regulate the charging power source so that the voltage is just above the battery's voltage. And as the battery's voltage moves, this chip will try to regulate the power source. Now, if you get to a point where there's no current and to get the proper voltage, then of course the charging will just shut off. Because the chip's smart enough. But the idea is this is the valuable feature that allows it to work with low power solar panels to charge the battery. You can find more details of this functionality too in the data sheet, and as well as how to set a resistance value if you want to have control over what the minimum voltage it'll take is. So I encourage you to check that out. The last thing I want to mention before I talk about charging the battery is this chip also has something called load mode, and I'm not using load mode. So the idea is when you don't have an input power source on V-bus or the charging power source, you can actually then have power flow the opposite direction to power some device. So I'm not quite sure what they had in mind with this, but I guess you could have you can input power to charge the battery, and then you can use, instead of having a separate output, you could use that same input to charge a device. So that's why they did it. Now, if you look in the data sheet, you'll see that this IC, the way they have bidirectional power flow is by back-to-back P-channel MOSFETs, just like we did for this solar panel. So I just thought that'd be interesting. And you can see the diagram of this IC in the data sheet. Now, I don't want to use load mode, so I followed their guidance in the datasheet, which just said tie the enable pin to power good. And so what that means is whenever there's not an input power source, because remember, power good signals the LEDs that you have good input power, power good will go to high impedance, which will cause enable not to not be enabled. So whenever there's no input power, this chip is set up to not be enabled. That way, those internal MOSFETs are going to be shut off, so battery power cannot flow this way. So I have this chip set up so power can flow only one way. And let me then talk about power good and charge, because I should have mentioned that first before I talked about this load mode and enabling it. The idea is these pins can allow you to have those two LEDs that I showed in my example, so you get an indication of what's happening. So the idea is these pins are high impedance unless you're actively charging or have a input good power. So here are the LEDs over here, and I have them labeled for charging and PG for power good. And the idea is I have them tied to the battery charge bus, and these pins, when you don't have good power, it'll be high impedance. So you'll get no current flow through the LED. But once you have a good power applied, then you get current flow through the LED and it turns on. Same with the charging circuit. This is not taking power from the battery per se, because they won't be on unless you have an input power source. If you're real picky on maximizing power, you could remove these LEDs. And then of course this output bus, this battery charge bus, the same bus the LEDs are connected to, that's where the battery is connecting after that mechanical switch is used or not used, in whatever case you want to do. So that's where the battery is connecting. So that's where we charge the battery. And of course, here is another Schottky diode, the same ones we saw on the previous schematic. So the battery voltage is always going to be lower than 5 volts, which is the input USB power. So that way, whenever you input USB power is in, this diode is not forward biased, so the battery is cut off from the circuit. When USB power is not applied, the battery voltage will forward bias this and power the boost regulator to get our output 5 volts. Now you are wasting a little power by using this diode. I had a pretty high capacity battery and I didn't want to make this design overly complex, so I'm just using a simple diode. If you wanted to be a little more power efficient, you can investigate using something like these back-to-back P-channel MOSFETs. Okay, well that's an overview of the charging circuit. Let's look at the PCB layout. So here's the PCB layout in my EagleCAD software. And the red traces represent top layer. So this is a 2-layer board. And the blue traces, like here, represent traces that are run on the bottom of the board. And then these blocks are the different components. You know, on each side we have, this is the input USB power. This is the output USB power. Here's where the solar panel connects. Here is the 5-volt pins if you don't want to use the USB to access the 5-volt out. This is the boost regulator circuit. This is the charging circuit all the way here to these P-channel MOSFETs, or these N-channel MOSFETs. Here's the P-channel MOSFETs. Here's those 3 test points I showed. Here's our charging IC. It's nice and compact and small. Here's our LEDs. Here's where the battery connector goes. Here's where that optional mechanical switch goes. And of course, we have these vias connecting the 2 ground layers. We have holes for mounting. And then the most work as far as layout is concerned goes into the boost regulator, because that's the device that's most sensitive to the layout. And if you want to learn more about that, I'm not going to go into it in this video, but I have a video where I use this exact boost regulator and I cover the PCB layout in more detail. I'll provide a link to that. Here we can look at the design with the ground layer showing. So you got to get a picture there. And so this is what, if you're a Patreon member, you can send in the files and get this made and use the BOM to buy the parts. But yeah, that's an overview of the design. I really had a good time with this design and I plan to iterate and use it for some of my own household designs. If you have any questions from this, please use the comment section. And if you think I missed anything or you want to add more, also use the comment section. That's it for part 2. Thank you for watching.